Hello students, welcome to Academy's platform for class 12 physics. In this module, we will consider a problem from radioactivity. So, radioactivity you have learned in your theory classes and you have solved quite a few problems. But here we consider a typical problem. To determine the half-life of a radioactive element, a student plots a graph of ln dNdt, ln mod of dNdt versus T as shown in this figure. Here dNdt is the rate of radioactive decay at time T. If the number of radioactive nuclei of this element decreases by a factor P after 4.16 years, find the value of P. So this graph is a plot of ln mod dNdt versus T. And I find this is a linear graph. Let us look at the relationship n has with T. You know n equal to n naught e to the power minus lambda T. It comes from the basic equation. Decay rate is actually proportional to n. N is the number of radioactive nuclei present at the time instance T, and the number naturally decays, disintegrates, and the rate of disintegration dNdt is proportional to n, and from that you write dNdt is equal to negative lambda n, where lambda is disintegration constant. And lambda has a unit of reciprocal of time. If time is in years, lambda will be 1 by year. Lambda's unit will be 1 by year. So lambda's unit is 1 by year if time is expressed in years. That you know. Now this is the basic equation. What n0 stands for? N0 is actually n is n0 at t equal to 0. Alright. Now from this equation, if I write dNdt is equal to n naught lambda e to the power minus lambda t with the negative sign. N naught lambda e to the power minus lambda t. So mod of dNdt, I can write all these quantities are positive quantities, n0 lambda. So it is n0 lambda e to the power minus lambda t. I think this is clear. So if I take ln of mod dNdt is actually minus lambda t plus ln n naught lambda. Alright. Now in the graph, ln mod dNdt is plotted against T. T is expressed in years. And you see it is the equation of a straight line looking like y equal to mx plus c. And the gradient of this straight line is nothing but gradient is equal to negative of lambda. Lambda, as I told, it is disintegration constant, radioactive disintegration constant. So this is there. Now from the experimental data, the student has plotted a graph, and from the experimental graph, I can find out the value of gradient of this particular graph. So here gradient is equal to how much? It is, take these 2 points on the graph. So you know it is y2 minus y1 by x2 minus x1. This is a famous gradient formula. So if I use that, so y2 minus y1, so 3 minus 4 divided by 6 minus 3 minus 4 divided by 6 minus 4. I hope it is clear. So it is negative of half. So this negative of half, as we have already theoretically established that for such a graph where ln mod dndt is plotted against t, the gradient of this line is actually negative lambda. Therefore, negative lambda is negative lambda is equal to negative half, or lambda is equal to half. And unit is r to the power -1. This much I know. Now, once I find lambda, then what is the question? If the number of radioactive nuclei of this element decreases by a factor p after 4.16 years, that means you start with this equation n equal to n naught e to the power minus lambda t. Now it decays by a factor p after 4.16 years. That means when small t is 4.16 year, n is nothing but n naught divided by p. So if we plug in these values in this equation, so it is n naught by p is equal to n naught e to the power lambda. I have already found half, so it is minus half into t is actually 4.16. Okay, so it is 1 by p. From this 1 by p is equal to e to the power minus 2.08. Alright, 4.16 divided by 2. Therefore, p is equal to e to the power 2.08. And e to the power 2.08 comes around 8.0043. So, value of p is p equal to 8.0043. That means the number of radioactive nuclei decays by a factor 8.0043 in 4.16 years. Therefore, the value of p is this much. So, this is the answer. So, I think you have clearly understood the steps over here. Using the decay formula and simple calculation and graph, we could find the value of p. So, this is the problem. Okay, if you find any difficulty in understanding, please revert back to us. We will take additional modules or lectures for this. So, with this, I conclude this module. Thank you. Thank you very much.